In science, not all chemical reactions happen instantaneously and in one step. Some chemical reactions are very complex and require several steps to come to completion. This is known as reaction mechanisms. Reaction mechanism is a series of elementary reactions or a series of steps which determine the reaction rate and when added together result in an overall balanced equation. An everyday example of a reaction mechanism could possibly be cooking Thanksgiving dinner. Cooking Thanksgiving dinner does not happen in one step. You have to cook a turkey, you have to cook vegetables, you need to make gravy. It's a series of steps. And it's those series of steps that determines how long it takes to cook the dinner. A single step in a reaction mechanism is known as an elementary process. A reaction intermediate or intermediates are a substance or substances which is produced by an elementary process only to be consumed by a later elementary process. The rate determining step or RDS is the slowest elementary process in the reaction mechanism. This step has the greatest activation energy of all of the elementary processes, and it's this step that determines the overall reaction rate. Let me go back again to my example of cooking Thanksgiving dinner or cooking a turkey dinner. You need to cook a turkey, you need to cook vegetables, and you need to make gravy. The rate determining step in those three processes would be the cooking of the turkey. That's the longest step and therefore has the greatest activation energy. As such, this step will determine the overall reaction rate. What that means is it doesn't matter how fast I can cook vegetables, it doesn't matter how fast that I can cook gravy, how long from start to finish is still dictated by how long it takes to cook the turkey. If I can make gravy 10 times faster, you're still not going to eat any sooner because I still need to wait for the turkey to cook. A catalyst, as we learned in the last lesson, is a chemical species that appears as a reactant and a product. It typically appears in the very first elementary process as a reactant, since a catalyst is a substance that we add to a reaction in order to speed it up, and it's not seen again until the last step as a product. However, this is not always the case. What you need to remember is that a catalyst is a substance that we add to a reaction, therefore it's going to appear as a reactant in one step, and later on it will appear as a product. Notice that it's the opposite of a reaction intermediate. A reaction intermediate is a product which is then later consumed in a further step in the elementary process. There are three different types of elementary reactions. There's unimolecular, where only one molecule reacts. Bimolecular, where there are two particles colliding and reacting and is the most common type. And then the least common type is termolecular, which involves three particles colliding and reacting. I always say that the easiest way to learn terminology is to practice. So what we're going to do now is we're going to go through the example on this page to help us practice some of the terminology that we learned on the last page. You'll notice here that I have a reaction mechanism. I know I have a reaction mechanism because this reaction takes place in more than one step. Each individual step is called an elementary process. So this reaction mechanism has three elementary processes since it has three steps. Additionally, I know that the second step is the rate determining step. The first step goes very fast, the third step is fast, and the second step is slow. So the second step is the slowest of those three, and therefore it's the rate determining step. When we want to analyze reaction mechanisms, we must first look at each elementary process and determine if there are any species in the entire mechanism that we can cancel out. Like math, if the species appears on opposite sides of our, and I am using quotations right now, equal sign, which is our arrow, we can cross them out. For example, HCO2H positive appears as a product, and then HCO2H positive appears as a reactant later on. It is an identical species that appears on opposite sides of our arrow, so we can cancel these out. Likewise, HCO negative and HCO negative, identical species on opposite sides of our arrow, it can also be crossed out. The last thing that we can cross out is our H positive. It appears on opposite sides of our arrow, therefore we can cancel it out. Whenever we cancel species, we're working with either an intermediate or a catalyst. Remember that an intermediate is a species that is a product first and then a reactant, and a catalyst is a reactant and then it becomes a product. I'm going to go through and cross these species out again, but as I cross them out, we're now going to classify them on if they're a catalyst or if they're an intermediate. So again, we have HCO2H positive. It is a product first, seeing as it's on the right-hand side of our arrow, and then it becomes a reactant since it's on the left-hand side of our arrow. The definition of a product first and then later on becoming a reactant is the definition of an intermediate. So I'm going to list that here. Next, we looked at HCO negative. HCO negative is a product first and then it becomes a reactant. Exactly the same as the last species, so this is also an intermediate. The last thing we crossed out was H positive. It was a reactant, and then later on, it became a product. That's the definition of a catalyst. So our catalyst would be H positive, and that also gets crossed out. In order to write the overall equation then, we write down whatever hasn't been canceled out. So we have HCO2H, and that goes to CO plus H2O. Let's look at the next example and go through the same processes. We're going to be looking at this reaction mechanism, and notice that this reaction mechanism has 4 elementary processes since it has 4 steps. We've been asked to identify any reaction intermediates and any catalysts, and in order to do this, we need to identify species that we can cancel or cross out. Remember that they have to be identical as if they were photocopied, and they have to be on opposite sides of our arrow. First, I see HOOBr, that is a product first, and then later it becomes a reactant. This is the definition of an intermediate. Next, I see that I have 2 HOBr on the product side, and I have 2 on the reactant side. They can cancel since there's 2 on opposite sides of our arrow. That is also an intermediate, so I'm going to write down HOBr. You don't need to write down the 2, we're just identifying it. So all of these species are canceled out. There's nothing else there that I can cancel out, so I do not have a catalyst. And sometimes that is a trick question, and we'll just answer that there are none. Then we need to identify the rate determining step, and this is where we look in order to identify the rate determining step. We're always looking for the slowest step. In our case, that would be the first one. Then, to give the overall reaction equation, we're going to write down everything that we did not cancel out. We also want to make sure that when we write the overall reaction equation, we give it in the lowest terms. Meaning, I see that I have HOBr as a reactant 4 times. I'm not going to write down HBr plus HBr plus HBr plus HBr. That's very repetitive and long-winded. I'm going to write down that I have 4 of them, along with oxygen gas, and that's going to give me 2 water molecules and 2 bromine. When we talk about the overall reaction rate, we're talking about how fast it takes for all of the steps in a reaction mechanism to occur. And the overall reaction rate is always equal to the rate of the rate determining step. Again, think of the analogy of cooking Thanksgiving dinner. No matter how fast you can cook, anything else in the dinner besides the turkey will have no effect on the overall reaction rate. If you want to eat faster than normal, you have to find a way to cook the turkey faster because that's the slowest step. So the rate of the overall reaction is determined by the rate of the slowest step. If the rate of the rate determining step changes, then the overall rate will change. The other steps have little to no influence on the overall rate. For instance, changes in concentration affect the overall rate only if the reactants whose concentrations are changed are present in the rate determining step. Decreasing the concentration of a reactant in the rate determining step will decrease the overall rate, and vice versa. Thinking back to what we talked about with relation to the collision theory. If you decrease the concentration, then there's less particles present in a given space. If there's less particles present, there's going to be less successful collisions with the sufficient energy and proper orientation, so the reaction rate will decrease. Let's look at an example. We have a reaction mechanism where we have two elementary processes. What can we cancel out? The first thing we can cancel out is I negative aqueous. It's a reactant and then it becomes a product. That's the definition of a catalyst. We can also cancel out IO negative aqueous. It's a product and then a reactant. That's the definition of a reaction intermediate. There's nothing else here that we can cancel out. What is the rate determining step? Well, the rate determining step is always the slowest step, and that would be step number 1. Will decreasing the concentration of hydrogen peroxide affect the overall rate? How so? Well, at first glance, this looks like a just straight up collision theory question from the last lesson. However, whenever we're working with reaction mechanisms or multi-steps, we must always first check to see if the species whose concentration we're changing is in the rate determining step. If it's not in the rate determining step, it's a trick question, as there will be no effect. However, after identifying the rate determining step, you will notice that hydrogen peroxide is in fact a reactant in the rate determining step. So by decreasing the concentration, we will have an effect on the overall rate. Therefore, we can say, yes, since hydrogen peroxide is in the rate determining step, decreasing the concentration will decrease the number of particles. So there will be less successful collisions with sufficient energy and proper orientation so the reaction rate will decrease. So remember that whenever you're answering questions about the rate as it relates to the collision theory, you will be required to write the entire recipe. Last, we can give the overall reaction by writing what we did not cancel out in lowest terms. So 2 hydrogen peroxides will decompose into 2 water molecules and an oxygen. Okay, let's try this one last time. Let's see what we can cancel out. I have 1 oxygen gas, and that can cancel out with this oxygen gas. Remember, that has to be identical. It was first a product, and then it became a reactant. That's the definition of an intermediate. We also have NO gas as a reactant, and then a product. That's the definition of a catalyst. Lastly, we have NO2 gas as a product and then a reactant. That's the definition of an intermediate. To write the overall reaction now in lowest terms, we have 2 O3 or 2 ozones, and that produces 3 oxygen molecules. Will changing the concentration of nitrogen monoxide affect the overall reaction rate? Again, at first glance, it looks like a straight-up collision theory question. However, we're working with a mechanism with multiple steps, so we must first check to see where nitrogen monoxide occurs to see if it's in the slowest step. Once you identify the slowest step, you will notice that nitrogen monoxide is not part of the rate determining step. If it's not part of the rate determining step, it will not affect the overall reaction rate. So no, since nitrogen monoxide is not in the rate determining step, changing its concentration will have no effect on the overall reaction rate. So be very careful when you're working with mechanisms to ensure that you don't fall into the trap of a trick question. Check to ensure that the species that they are talking about appears in the rate determining step. Remember, this only works for mechanisms. The last thing in this chapter that you have to be able to do is to draw and interpret potential energy diagrams for reaction mechanisms. Until now, we've learned how to draw a potential energy diagram for a single step. Since a reaction mechanism is multiple steps, you'll notice that a potential energy diagram for a reaction mechanism looks like multiple potential energy diagrams strung together. Notice the potential energy diagram for the reaction mechanism given in the notes. There is a couple of things that you can determine from this potential energy diagram. For instance, the first thing that we'll notice is there's 3 elementary processes. 1, 2, 3 bumps means that there's 3 steps in this reaction mechanism. The next thing I know is that step number 2 is my rate determining step since it's the highest hill. Therefore, it requires the most energy and will be the slowest. Therefore, it's the rate determining step. I also know that the overall reaction rate is an endothermic process. I know this because starting with the very first reactant and ending with the very last product, the overall shape is endothermic. The potential energy of the products is higher than the potential energy of the reactants, so in order for this to happen, overall, we had to put energy into the reaction. Since the second step is the rate determining step, it's also the second step that has the overall activation energy. So this is where EA overall will appear. It goes from the reactant of step 2 to the activated complex of step number 2. This is the activation energy for the overall because this is the energy barrier that must be overcome in order for the overall reaction to occur. This brings us to the end of the lessons on the kinetics chapter. Please attempt the worksheet that appears after this section and prepare yourself for an assessment on kinetics.